Hi, I'm Shrestha Sangamala, ID 1174477957. I'm here to present the final project for the course ADTA 5550 AI Deep Learning with Big Data, which I have taken for summer 2021 in University of North Texas, Denton. For the next 20 to 30 minutes, I'll be explaining about the introduction of my project, architecture of my project, data and data set and workflow that I have used for my project, the results, and finally the conclusion for my project. Coming to introduction, first I want to explain what is deep learning. Deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain called artificial neural networks. Deep learning has become popular as the models are capable of achieving state-of-the-art accuracy. Large size data sets are used to train these models along with the neural network architectures. Deep learning is using brain stimulations, hoping learning to make algorithms more efficient and simpler to use. I discussed some more few points like what is the difference between deep learning and machine learning. In deep learning, the performance of the model increases as amount of input data increases. Whereas in the machine learning, the performance graph of machine learning model increases and does not improve with increase in the amount of input data beyond a point. And in deep learning, deep learning advocates like solving a problem into the end, whereas in machine learning, a problem is break down into parts and solve each problem of part and combine all parts to get the final result. Testing in deep learning takes much lesser time, whereas testing a machine learning model takes much longer time as compared to deep learning model. I would like to discuss more about the supervised learning and unsupervised learning. These two, supervised and unsupervised learning, are two different categories under supervised learning. Under supervised learning, convolution neural network CNN and recurrent neural network RNN and artificial neural network ANN are considered. Under unsupervised models like autoencoders, Boltzmann machines, self-organization machines, these are two different, but most of it has distinct features uh, but the most integral point of difference is how these models are trained. While supervised models are trained through examples of a particular set of data, but the unsupervised models are only given input data and does not have a set outcome. They can learn from, so that column that we are always trying to predict is not there in any unsupervised model. While supervised models have tasks such as regression and classification and will produce a formula, but in unsupervised models have clustering and association rule learning. So these are some of the important models I would like to discuss about. Coming to the architecture of artificial neural network and RNN, recurrent neural network, and the CNN, convolution neural network. Coming to ANN, artificial neural network. What is an artificial neural network? It is also called as feed-forward neural networks because its input are processed only in the forward direction. This is actually group of multiple precipitators or the neurons on each layer. Some of the advantages in this is it is capable of learning any nonlinear function. Hence, these networks are popularly known as universal function approximators. One of the main reasons behind the universal approximation is the activation function. I would also want to discuss about the couple of challenges with artificial neural network. While solving an image classification problem using artificial neural network, the first step is to convert a 2D image into a one directional vector prior to the training itself. This has like two drawbacks. The number of training parameter increases drastically with an increased size of any image. Artificial neural network loses the spatial feature of the image. Coming to RNN has a recurrent connection on the hidden state. This looping constraint ensures that sequential information is captured in the input data. We can use RNN to solve problems like time series data, text data, and audio data. So some advantages of these are like RNN captures the sequential information present in the input data, that is the dependence between the words in text while making prediction, and also if you see the output of each time steps depends not only on the current word but also on the previous words also, and in RNN this shades the parameters across different time steps. This is popularly known as parameter sharing. Also, this RNN application has few challenges. One of the common is it suffers from the vanishing and exploding gradient problem. This problem is usually a common problem for all type of neural networks. Uh, Coming to the convolution neural network, I would like to discuss more in detail about uh, the the structure of this. As my project involves more of a convolution neural network, I will give more detail about CNN. Let's see what is CNN. Is This is a convolution neural network refers to a subcategory of neural networks. Therefore, they will have all the categories of neural networks. However, convolution neural network is designed to process input images. Their architecture is more specific, and it is composed of two main blocks. If we break down the first block makes the particularity of this type of neural network since it functions as a feature extractor. To do this feature extraction, in the template, matching by applying a filtering operation, the first layer filters image with several convolution kernels and returns feature maps, which are then normalized or resized usually. So this process can be repeated several times. We filter the feature maps obtained with the new kernels, which gives us new feature map to normalize and resize. We can also filter again and again and so on. Finally, the values of the last feature map are concatenated into a vector. This vector defines the output of the first block and the input to the second block. Coming to the second block is a characteristic of CNN. It is, in fact, at the end of all neural network used for the classification, the input vector values are transformed with several linear combinations and activation functions to return a new vector to the output. Thus, this last vector contain as many elements as they are classes elements. Different elements in this, each element is therefore between 0 and 1, and sum of all the world worth is equal to 1. These probabilities are calculated by the last layer of the block and therefore of the neural network, which uses a logistic function or a softmax function as an activation function. As gradient backpropagation, the cross entropy is minimized during the training phase, but in case of convolution neural network, these parameters refers in particular. Let's discuss about the different layers in convolution neural network. There are mainly four different types of layers for a convolution neural network. The first would be the convolution layer. The next is like a pooling layer. And next is the ReLU, the activation correction layer. And then the fully connected layer. Coming to the first, that is the convolution layer. The convolution layer is the key component of neural networks and is always at least their first layer, as I said. Its purpose is to detect the presence of a set of features in the images received as input. This is done by convolution filtering. This principle is to drag the window representing the feature on the image and to calculate the convolution product between the feature and each proportion of scanned image. So a feature is then seen as a filter. The two terms are equivalent in this context. The convolution layer thus receives several images as input and calculates a convolution of each of them, which each filter, these filter correspond exactly to the filters we want to find in a particular image. Now that we get for each pair, which is image, and filter a feature map, which tells us where the features are in the image. The higher the value, the more corresponding place in the image replaces or resembles the feature. Coming to next layer, which is pooling layer. This type of layer is often placed between two layers of convolution. It receives several feature maps and applies the pooling operation to each of them. The pooling operation consists in reducing the size of the images while preserving their important characteristics. To do this process, we cut the image into regular cells and we keep the maximum value within each cell. Usually, smaller square cells are often used to avoid losing too much information. The pooling layer generally reduces the number of parameters and calculations in the neural network. This improves the efficiency of the network and avoids learning. Coming to the next layer, the correction layer, which is an activation filter. The ReLU correction layer replaces all the negative values received as input by 0. It acts as an activation function. Uh, the last layer would be the fully connected layer. The fully connected layer is always the last layer of the neural network. Convolution or not, this type of layer receives an input vector and produces a new output vector. To do this, it applies a linear combination and then possibly an activation function to the input value received. Lastly, the last fully connected layer classifies the image as an input to the network and it returns a vector of size n. where n would be the number of classes in a specific image classification problem. Each element of the vector indicates the probability of the input image to belong to a class. The convolution neural network learns that the weight values in the same way as it learns the convolution layer filters during the training phase by back propagation of the gradient. Coming to the next. So as the first part of assignment, we need to find a data set that consisted of images or audio files that was also able to perform deep learning. So I found a chest X-ray dataset. It is an image-based dataset, and this dataset is collected from Kaggle.com. And this dataset consists of 5,863 X-ray images of two categories, pneumonia and normal. This dataset is organized into three folders. They are train, test, and validation. You can see in the image of the data set in this image here in the right. Coming to the part 2 of the data set. So next we need to we are going to do what the majority of my project is like building, training, testing, and developing a convolution neural network for the CIFAR-10 dataset. Uh, so there are around 60,000 images of animal vehicle classes, and there are also labels. So each image is a colored image. So there is three color channels, and size of image is 32 by 32 by 3. And there are like 10 classes with 6,000 images per class, and they are coded as from 0 to 9. And there are, as discussed, there are 10 classes in the data set. They are like aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. The data set is classified into two categories. There are 50,000 images in the training set, and around 10,000 images in the testing set. In this picture, we can see some of the samples images in each class in the CIFAR-10 dataset. So before we able to build our neural network, we had to first download the data set and combine it into a virtual machine. And then we will upload the data set to the Python. So I uploaded all the files for CIFAR-10 dataset, which are batches.meta, data batch 1 to data batch 5, and test batch to the SSH, and then copied files to the subfolder created as like a cipher underscore 10 underscore data in JP underscore Jupyter notebook, like JP underscore NTBK folder in my virtual machine. This is as shown like this. Next, then I open the Jupyter notebook server in the remote virtual machine, and you can see the dataset in the CIFAR-10 data subfolder present in the Jupyter notebook folder. And these are the data files of the CIFAR-10 dataset. As of now, we understood the data set and downloaded the data set from Canvas and uploaded it into the Jupyter Notebook server. For the next part of the project, we need to build, train, and test a convolution neural network on CIFAR-10 dataset. So this is the diagram I created to show the convolution neural network with CIFAR-10. with two convolution layers. The first part of the diagram is the input, and it was a size of 32 by 32 by 3. It is 32 by 32 because that is the actual size of the image that is being input to the model, and 3 because the image is on a color scale. That means there are three color channels. So the first convolution layer was 28 by 28 by 6, and the first pooling layer was as 14 by 14 by 6, and the second convolution layer with 10 by 10 by 16, and the second pooling layer is like 5 by 5 by 16. So after all the convolution and pooling layers were created, the last pooling layer was flattened, and to go into the model for it to be trained and tested, there are three fully connected layers in this model. And by importing the data to Python and defining all the supporting functions to build, train, and test the CNN model, which I created as discussed. I set up all required convolution layers to my model, and I want to check the accuracy of my model. So I ran the program in the Python, and the results are as follows. There are like 49 steps with each step of 100. For the initial step, there is about 10.3% accuracy, and it gradually increased up to a step 10 to like around 60.6 percentage. And from the 10th step to the last step, it is increased from 60 to 68%, 68.34%. and and we can see the test accuracy, average accuracy is around 62.43 percentage for the Cipher 10 dataset. So the next step of the project is comparing the convolution neural network developed for a Cipher 10 dataset and the convolution neural network model we created for the MNIST dataset in one of our assignments. These two datasets have a lot in common, as they both are image datasets, and they strive to achieve the same output. They are like both image datasets, and they want to produce a label as their output. And as already discussed, the Cipher 10 dataset has around 60,000 images with 50,000 in training and 10,000 in testing. And the images are from the around the vehicles and animals, valued labeled from like 0 to 9, and there are like 10 classes in Cipher 10 dataset, and images are of size 32 by 32 by 3. Whereas in MNIST dataset, there are 70,000 images, in which 60,000 are from a training data set and 10,000 images are from testing data set. These images are handwritten digit images, which label like 0 to 9, and they are also a grayscale images with black and white, and these images are size of 28 by 28 by 1. So they are a little bit smaller than the Cipher 10 dataset. These are some examples for the Cipher 10 dataset, like a truck, and here it's like a vehicle. And these are the examples for the MNIST dataset. These are like handwritten digits, like 504. Next, in this slide, I want to discuss about the CNN model for the two datasets, Cipher 10 dataset and for the MNIST dataset. The convolution neural network structure for both the models are similar, but the only difference is the size of the input image. For Cipher 10 dataset, it is like 32 by 32 by 3, which is bigger than the input for the MNIST dataset, which is around 28 by 28 by 1, which is smaller image. The first convolution layer was 24 by 24 by N1. The first pooling layer was 12 by 12 by N1, and the second convolution layer was 8 by 8 by N2, and the last pooling layer was 4 by 4 by N2. And the last one went by like 5 by 5 by 16. And then they both are connected to the flattened into a one-dimensional vector to get fit into the fully connected layers. But the size is different overall in the model. And in this slide, I'm going to discuss about the output accuracy for the both data sets. These are like steps 0 to 49 for the both Cipher10 and MNIST. The difference from step 0 to step 10 is in the Cipher10 is from 10% to 60%, whereas for MNIST it is around 9% to 98%. There is a drastical difference in accuracy in first 10 steps in MNIST dataset, but from step 10 to 49, it increased from 60% to 68%, whereas in Cipher10 dataset, in Cipher10 dataset, but 98 to 99 in MNIST dataset. We can see there is a very little difference in MNIST dataset compared to the Cipher10 dataset. This is due to the size of the image input to Cipher10 is comparably bigger than the input to the MNIST dataset. If we plot the Cipher10 and MNIST dataset accuracy, there is we can see like there is a drastical change from step 0 to step 10 in and from 0 to 90 around 90s in MNIST, and whereas in Cipher10 we can see like a 0 to 40 and then 40 to 50, and it has gradually increased up to 68%. Comparing the Cipher10 and MNIST datasets accuracy, I think the following possibilities are considered, because as we are using the convolution neural network architecture for both the datasets, accuracy will change because MNIST dataset is a grayscale, while a Cipher10 dataset is a colored images. We have used filter size of 5 by 5 for both the models. There is a change of gap in the test results. In future, we can try with other filter sizes to vary our results. For MNIST, model was trained for 5,000 steps for batch size of 50 was considered. And after every 100 steps, we make the model to evaluate and test data. But the Cipher10 model was trained for 5,000 steps, but the image batch size of 100 was considered. And after every 100 steps, we could make model to evaluate and the test data. I also feel like dropout a layer probability value matters a lot for accuracy difference for both the data sets. Coming to the final part of my project, it is to redesign the architecture for the Cipher10 dataset. So I added one more convolution layer and a pooling layer to the existing convolution neural network model. So there are total of 3 convolution layers and the 3 max pooling layers and 1 flattening layer and 1 fully connected layer and 1 output layer. I want to check how the accuracy will increase by adding 1 convolution layer to the existing CNN for Cipher10 dataset. And I ran the program in the Python, and the following are the results. By redesigning the CNN model for Cipher10 dataset, I got accuracy of around 72%, which is better than the original model. So it is understood from this, if we add more layers, then model will learn more, and there is a chance of achieving good accuracy and validation data, which will not make model leads to overfitting, and we can attain good test accuracy as well. Coming to the conclusion, this project compares the model performance between the original CNN models with the redesigned CNN models on a Cipher 10 dataset. Approach of using a redesigned convolution neural network model is better than original model to boost up the performance of the model. This result can be still improved with the help of a pre-trained model or performing hyperparameter tuning. In future, with increasing the depth of the CNN model and with the help of pre-trained model, we can increase performance of model. Other features, extraction methods can also be used, such as using a transfer learning to extract features, and we can get a good test accuracy. Thank you.